Section: Introduction. In this section, we discuss recent models like DeepSeek R1 and O3, which have shown impressive results in reasoning tasks such as math, coding, and science. These models typically begin with a strong foundational model and enhance their reasoning abilities through post-training methods like supervised fine-tuning, SFT, or reinforcement learning, RL. This post-training allows the models to generate extended reasoning sequences, or thinking tokens, that help them arrive at correct answers. However, the detailed methods for these advanced reasoning models are not publicly available, complicating the development of new reasoning models. We recognize that improving SFT data curation is a crucial strategy for creating effective reasoning models. For example, the DeepSeek R1 Distill models demonstrate that combining a base model with a well-curated dataset of question-answer pairs can lead to top-tier results on benchmarks, achieving 51% on AMY and 33% on GPQA without additional RL steps. Other works, like Sky T1 and S1, use similar model architectures and training setups but still enhance performance by refining their training datasets. These cases underline the significance of high-quality SFT data in boosting reasoning performance. However, many projects only explore a small range of design options, such as using human-generated questions or relying solely on DeepSeek R1 as a teacher. To recreate reasoning models effectively, we need to investigate a broader range of strategies for generating question-answer pairs. Unfortunately, this exploration can be costly due to the expenses associated with teacher inference and model training. As a result, many researchers depend on existing heuristics and intuitions for their data design choices. Our goal with the Open Thoughts project is to clarify the SFT data curation process and better understand what makes a strong reasoning SFT dataset, challenging existing beliefs about data quality. To achieve this, OpenThoughts 114K examines how scaling the Sky T1 pipeline with automated verification enhances performance. OpenThoughts 2:1M builds on these improvements by increasing data scale through diverse question generation, including synthetic questions. We also conduct empirical investigations into data curation techniques to enhance reasoning capabilities, performing over 1,000 experiments across math, code, and science domains. This leads us to develop a simple, scalable, and effective pipeline, which we scale up to create OpenThoughts 3:1.2M and fine-tune Qwen 2.5-7b instruct on it, resulting in OpenThinker 3-7b. As shown in our results, OpenThinker 3-7b stands out as a leading open data model at the 7b scale across various reasoning benchmarks, outperforming the R1 Distill 7b model by an average of 12.4 points across 12 tasks and surpassing the next best open data model, Nemotron Nano-8b, by 2.1 points. We share our models and data with the community, along with key findings from our research. Some insights include that sampling multiple answers per question from a teacher model can significantly expand the dataset, leading to notable performance improvements. We also found that better performing models are not always better teachers, as seen with QWQ32b being a stronger teacher than DeepSeek R1 despite lower scores on reasoning benchmarks. Our experiments with various verification and answer filtering methods did not yield significant performance gains. Additionally, selecting questions from a few high-quality sources resulted in better performance than optimizing for diversity. Finally, filtering questions based on difficulty or response length from language models produced better outcomes than traditional pre-training data curation methods. In the related work section, we note that the introduction of models like Gemini, QWQ, and DeepSeek R1 has enabled the training of smaller models through the distillation of reasoning traces from larger models. DeepSeek has released effective distilled models alongside DeepSeek R1, showcasing the potential of this approach. Many open data initiatives have since aimed to replicate these models by creating SFT reasoning datasets from teacher models like QWQ32b or DeepSeek R1, focusing on math, code, and science. Datasets such as OpenR1, Open Math Reasoning, and Open Code Reasoning gather questions from public forums and competition sites, while others like natural reasoning use large pre-training corpora to generate reasoning traces. Projects like S1 and Limo emphasize the manual curation of small, high-quality datasets. Overall, many reasoning projects introduce innovations across various stages, including data sourcing, filtering, and scaling, while some works focus on building reasoning datasets for reinforcement learning. Section Summary. In this section, we discuss recent advancements in reasoning models like DeepSeek R1 and O3, which enhance performance in math, coding, and science through post-training techniques such as supervised fine-tuning and reinforcement learning. We emphasize the importance of high-quality data curation for training these models and introduce our Open Thoughts project, which explores innovative data generation strategies and demonstrates significant performance improvements in reasoning tasks with our OpenThinker 3-7B model. Section: The Open Thoughts Project. In this section, we introduce the Open Thoughts project, which aims to develop advanced open reasoning datasets. We focus on identifying the best questions and answers that promote reasoning. We began with BESPOKESTRATOS17K and have evolved through 4 versions, leading to OpenThoughts 3-1.2M and OpenThinker 3-7B. We share our findings with the community, and OpenThoughts114K showcases the benefits of scaling effective dataset generation strategies. We started with BESPOKESTRATOS17K and expanded it by sampling more questions from sources like Taco, apps, and code contests. This dataset includes 114,000 questions across various subjects, 89,000 in math, 20,000 in code, 4,000 in science, and 1,000 in puzzles, with answers derived from DeepSeek R1. Our tools ensure the accuracy of math and code answers through answer matching and unit tests, filtering out incorrect reasoning traces. OpenThoughts 2-1M was our first attempt to reach 1 million entries, incorporating new sources like AutoMathText and OpenR1. This dataset produced a model that competes with R1 Distill 32B, even surpassing it by 6% on the AMY25 benchmark. We used 600,000 verified samples from OpenR1 Math and 200,000 unverified samples from various math and code sources, selecting the best performers from 26 sources. OpenThoughts 3-1.2M, which we focus on in this paper, reflects the insights gained from earlier datasets and our systematic exploration of the dataset design space. We will detail the data pipeline and the final dataset composition. For the OpenThoughts 3-1.2M data pipeline, we outline our experimental setup for training and evaluation, comparing data strategies in a controlled way. We analyze each step of the pipeline independently and choose the best strategy based on performance. Our goal is to create the most effective dataset of question-response pairs for reasoning. We systematically test each step of our pipeline, generating 31,600 data points for each strategy and fine-tuning the Quen 2.5-7B and struct model on these datasets. We selected this scale to balance cost-effectiveness and meaningful results, choosing 31,600 as a midpoint between 10,000 and 100,000. We evaluate our models using reasoning benchmarks for math, code, and science. The benchmarks include AMY24, AMC23, and Math 500 for math, Code Elo, Code Forces, and Live Code Bench for code, and GPQA Diamond and JEE Bench for science. We score each model based on average performance across these tasks, using Evalchemy as our primary evaluation tool. We also clean our datasets by removing samples that are too similar to our benchmarks. In our pipeline, we select the best performing approach at each step based on average benchmark scores. Unless stated otherwise, we generate answers using DeepSeek R1 as the teacher model. The first step in our data generation pipeline is sourcing questions for each domain. We categorize our sourcing techniques into 3 types: fully synthetic, where an existing language model generates questions with minimal seed material; semi-synthetic, where an LLM uses existing data as seeds; and non-synthetic, where humans write the questions. We cover 27 sources for code, 21 for math, and 14 for science. For our experiments, we generate 31,600 questions from each source, repeating questions as needed to meet this number. We use GPT-4o Mini for generating questions that require an LLM and DeepSeek R1 for generating responses. Our results show that code golf questions and competitive coding questions perform well in code, while LLM-generated and human-written math questions score highest in math benchmarks. In science, physics questions from Stack Exchange and LLM-extracted questions from textbooks achieve the best scores. Overall, simpler synthetic methods often perform as well as or better than more complex approaches, providing a solid foundation for the next stages of our pipeline. Section Summary. In this section, we introduce the Open Thoughts project, which aims to develop advanced open reasoning datasets by systematically exploring question and answer generation strategies, culminating in the OpenThoughts 3 to 1.2M dataset. We detail our experimental pipeline for dataset creation, including training and evaluation setups, and highlight the effectiveness of various question sourcing techniques, demonstrating that both synthetic and human-generated questions can yield high performance across math, code, and science benchmarks. Section: Mixing Questions. In this section, we discuss how to effectively combine high-quality questions from various sources. We face the decision of whether to use a single best strategy or to mix multiple strong strategies to enhance performance. This mixing approach is crucial in our generation pipelines. While adding more question sources can increase diversity, it also risks including lower quality strategies. Our experiments aim to determine if the added diversity is worth the potential drop in question quality. To simplify our process, we use the rankings from the previous step to select candidate datasets. We choose the top-ranked datasets, randomly sample a set number of questions from each, and combine them into a larger dataset. Our findings indicate that mixing more than two sources tends to lower performance, with the best results coming from using at most two sources. Specifically, using two high-quality code question sources instead of 16 strategies leads to an average accuracy increase of 5% across all benchmarks. Next, we focus on question filtering. Given that each source can have millions of questions, it's impractical to train on all of them. Therefore, we need to select a high-quality subset. We explore various filtering methods, such as classifiers and difficulty scores, to improve dataset quality. Our experiments show that the two most effective filtering methods are difficulty-based filtering, which retains the hardest questions, and response length filtering, which selects questions based on the length of the answers generated by a language model. For math and code, the best filtering strategy improves performance by 4 and 6%, respectively, compared to random filtering. We also examine deduplication and the sampling of multiple answers per question. Deduplication helps enhance dataset quality by reducing repetition. We test different levels of deduplication and find that while it improves question diversity, querying the teacher multiple times for answers increases answer diversity. We explore various combinations of deduplication and answer sampling, and our results show that for code and science, different combinations yield similar outcomes. For math, the best strategy is exact deduplication with a specific number of answers per question, while for code, we choose a strategy without deduplication but with the same number of answers. Overall, we find that the benefits of question diversity may be limited for the reasoning datasets we evaluate, leading us to select the optimal strategies for each domain. Section Summary. In this section, we explore the effectiveness of mixing question sources and find that using at most two high-quality sources yields the best performance, with a 5% accuracy increase compared to using 16 strategies. We also investigate various question filtering methods, concluding that difficulty-based and response length filtering significantly improve dataset quality, while deduplication and sampling multiple answers enhance answer diversity, with optimal strategies identified for different domains. Section: Answer Filtering. In this section, we explore answer filtering, which involves verifying or removing low-quality annotations, a common practice in reasoning data pipelines. We believe that eliminating potentially incorrect data should enhance performance in subsequent tasks. Our experiments test various answer filtering techniques. To maintain a dataset size of 31,600 after filtering, we first generate 63,200 answers, apply each filtering strategy, and then sample 31,600 question-answer pairs from the filtered results. We also include a baseline with no filtering, which contains all 63,200 questions. Our findings for math datasets indicate that the random filtering baseline performed better than all other methods. For code question-answer pairs, the fast text classifier was the most effective filtering method, using positive examples from code forces answered with DeepSeek R1 and negative examples from those answered with GPT-4o Mini. In science, retaining the top 8 longest answers proved to be the best filtering strategy. However, across all domains, the no-filtering approach yielded performance similar to that of the filtering methods, suggesting that the advantages of filtering do not justify reducing the dataset size. Next, we discuss the teacher model used in our experiments. We utilized DeepSeek R1 as the teacher model, which is standard for many reasoning datasets, but we also considered other models like 5-4 Reasoning plus 14b and QWQ32b. Our experiments assessed the impact of different teacher models on performance, keeping sampling hyperparameters consistent. Results showed that QWQ32b outperformed all other models, achieving an average accuracy increase of 1.9% for code and 2.6% for math, despite scoring lower on average compared to DeepSeek R1 in specific benchmarks. We then scaled our pipeline to create openthoughts 3 to 1.2m, a dataset with 1.2 million samples. We found that scaling is crucial for strong performance, and we identified the best strategies at each pipeline step, plotting their performance as we increased the dataset size from 316 to 31,600 examples. Our results indicate a positive correlation between scale and performance, suggesting that larger datasets could lead to even better outcomes. openthoughts 3 to 1.2m consists of 850,000 math, 250,000 code, and 100,000 science data points, following a ratio similar to that of openthoughts 2 to 1m, which performed well with the DeepSeek R1 distill models. To achieve the desired sample sizes in each domain, we estimated the number of questions needed at the start of the pipeline, increasing the input math questions from 1 million to 3 million. We applied the best performing strategies at each stage, choosing more scalable options when performance was equal. The construction process for openthoughts 3 to 1.2m is illustrated in our figures. Our results show that OpenThinker 3 to 7b is the top open data reasoning model at the 7 billion scale, regardless of the optimization algorithm used, and it performs well on various evaluations throughout the pipeline. Further details on scaling can be found in the appendix.